Hello everyone and welcome to Module 5 in Big Data Technologies. We'll start with the module overview. So in this module you're going to have the opportunity to work with Apache Scala and Spark. So the Spark framework, the idea is to evaluate the operation of data frames in the context of Spark and Spark programming, apply the concepts of using parallel programming, and critique the creation of the RDDs, so your resilient distributed data sets, from both an existing and an external source. So starting, what's Spark? A good question. And the short answer is it's a high-performance distributed framework that handles parallel programming in a fairly straightforward way. The reason to use it is that it's simpler than writing a lot of concurrent distributed programs. It's always a good idea to leverage a framework instead of building your own from scratch. So definitely something to consider as an alternative. And the common uses are varied. It is an extensive set of frameworks. It's used from everything from analytics to data wrangling to machine learning, graph processing, and big data in general. So what is it from a different perspective? So looking at the layers of APIs. And this is taken from Spark, the Definitive Guide, definitely the book for Spark. So it is the one source to go to from a perspective of a resource, and it is available in our O'Reilly library, so worth taking a look at. So taking a look at the kind of layers of it, at a very low level is RDD and distributed variables. You almost never go there. That's not something that's commonly done. A step above that is the structured APIs, which is datasets, data frames, and SQL. Of those, datasets is almost down at the lower level, right? Generally speaking, you're going to be working with data frames and SQL. On top of all of that, you have a set of kind of workloads that it can do, which is advanced analytics. There's a bunch of libraries out there, ecosystem, and generally structured streaming. One of the cool things with Spark is that it does allow you to do both structured streaming and batch processing in the same environment. So some key things to kind of go over, foundational elements to talk about. RDD, it's the heart of Spark, and it's a resilient distributed data set. The idea is that they keep track of the operations that are done in a distributed way such that if something happens, say one of the nodes in your cluster goes away, becomes unavailable, goes offline for a while, and then comes back, maybe due to a partitioning issue with the network, whatever the thing that might happen, it's possible then to have another node pick up what that node had been working on and recompute it based upon what's essentially the series of operations that are defined in the RDD, not necessarily the data. The data is redone as it's needed using lazy evaluation, but it is something that can allow for essentially fault tolerance. The resilience is that whole key piece. It's that data sets have the capability of being recomputed at the point an RDD is needed, so that you can redo them as needed. RDDs are immutable in nature, which means you don't change them. You change through transformation. You take the output of one operation, applying it to an RDD, which produces another RDD, excuse me, which is what you then use for future processing. So you don't make changes, you transform and output. And that makes the creation of a graph much simpler from a operations perspective. Pretty much any external data set that's supported by Hadoop can potentially be used via RDD. They are low level, almost never used. And they're there, but its significant performance can be done using data frames because there's the concepts of caching and a few other things that have been built in. So generally speaking, you only use an RDD if you're doing something really quite interesting. The data frame is the most common one that you're going to be using. You take a file, you do a read into a data frame, and then you do some operation on it that results in an action because it is all lazy. So in this case, we're basically telling it to read the file. That may or may not happen at the point you issue that command. More likely than not, it will happen at the point that you call that take 3, which is essentially similar to a head on the files. So you're getting 3 items from that data set or that data frame. Notice also that you're interacting with it Spark dot something, right? So sometimes there's this Spark context that will be created for you depending upon where you're writing your code at. You may have to do it yourself, or if you're using something like Databricks, it's kind of inherently there for you. But the Spark context has a read operation, and then you give it some options such as inferring the schema. Header is the first row, a header. And then what's the name of the file in some path, right? So you basically can read it. And it does return back a list. A data set. This is something that only is available to you if you're writing code in Java or Scala. Scala runs on top of JVM, so Java Virtual Machines. It is a slightly different flavor. It's a different language than Java, but it was kind of inspired by it and kind of comes from it, but certainly runs on those machines. The benefit of that is then that you get a broad distribution base and so on. But generally speaking, a data set will not perform as well as a data frame. And you only use it if you can't use data frames for some reason. So maybe there's some function you're needing to use that is only available for data sets. That's why you would use it. Otherwise, stay in the world of data frames. So another concept is parallel programming. And what does that mean? And it's comparing it to distributed and concurrent multi-threaded programming. The course materials, I think, introduce an artificial sort of terminology here. Parallel programming simply means it's essentially the same thing as multi-threaded or concurrent programming. Things are happening at the same time. The question is if you're using a framework or not. That's the key difference. And distributed means not only are they happening at the same time, they're happening in different computers, right? So we first had multi-threaded and concurrent programming on a single processor at the point that we had or on a processor in a computer, at the point we had multiple processors inside of a piece of hardware. Up until fairly recently, that was really expensive. Back around 2000, I wrote a book around .NET multi-threading. I actually had to purchase a true multi-processor server from eBay or someplace. I forget exactly where I bought it. It was not a very high end, but it was a server that had more than one processor, because at the time the processors in our computers were single processors with single cores. Somewhere along the way they figured out how to put multiple cores onto the same chip, so you had true multi-threading on the same computer. But prior to that, you needed to spend a bunch of money to go buy a piece of hardware that had more than one processor, right? And it's hard is the short version. When you don't have a framework and you're writing code using primitive constructs in a programming language, whatever the language, it's pretty difficult to do. It's lost popularity in part because it was very hard to get a multi-threaded application that did concurrent processing to execute correctly all of the time, because there's all these kind of weird race conditions that can occur, and you have to balance locking for concurrency control without diminishing performance greatly. And the programming languages that we were using at the time, it was an afterthought. It was never something that was intended that you would just say what needed to happen and it happened. Not so much you had to go through the details yourself. So that was a lot of the issue. And the key takeaway from that whole conversation is whenever you see something that says concurrent programming, they're probably meaning multi-threaded programming on a single computer. Distributed programming is concurrent programming that's happening on probably a cluster, though you could have variations on those themes where you could write your own code that did distributed processing and concurrent processing, but it would be a real bear to write, so you probably don't want to do that. So instead, we used frameworks, and that's where things like Spark, MapReduce, and so on became very popular, because they made it to where a person that understood how to write essentially a callback function could then produce a parallel program or distributed program in the case of MapReduce. So you basically set up your mapper, set up your reducers, tell it that that's what those things are, and it called them in the appropriate way on the appropriate nodes. So it made it a whole lot easier. The same thing is somewhat true with Spark from a different perspective. With Spark, you basically say what needs to happen, but it is a lazy evaluation sort of thing where they only happen when they have to happen. And it still uses a language construct that's very familiar without introducing some artificial begin parallel block here, end parallel block here, and all this other stuff, to where you basically just say, I want to take this data set, I want to sort it, I want to select these columns, and I want to aggregate across these other values and produce this summation or something. And it figures out from that the graph of operations to perform, how it can perform them using an optimizer, distributes it across a set of nodes in a cluster. They do the work and pull it back together at the end and write it out to a file system. So that's one of the key kind of concepts here is whenever you're dealing with big data, you're going to have to do distributed processing most likely just because of the nature of things. Part of the definition of big data is that it is something that can't be done using traditional techniques. Traditional techniques is one big box with lots of power, right? So that's the basic idea. So inherently, big data equals distributed processing. We talk about forces and factors that are driving adoption of parallel and distributed programming. And these are kind of an important thing to think about from a how did we get here perspective, right? First, solid state drives. They've made it to where accessing data from mass storage versus memory is not that much different. So especially if you have hybrid combinations of solid state caches essentially on a disk-based drive, so you get the huge amounts of storage but also get the fast access using some sort of a persistent cache using the solid state part of the drive. In a hybrid drive sort of technology, you can get incredible performance with huge amounts of storage. We also had lots of advancement in multi-core processors, so basically adding not just multiple cores into a physical chip, but also virtual cores on top of those physical cores. So if you have physically have potentially like 4 cores, physical cores in your chip, you can easily have 2 essentially virtual processors per core, so up to 8 cores. That makes for a very compelling argument. Also throw in virtualization technology where you can essentially share that across multiple instances as needed, and you end up with a lot of computational power that can be shared in a managed way across multiple consumers in a large operation. Also been a lot of improvements around I/O parallelization, being able to get data due to networking advancements, and as well algorithms have made a huge difference as well. Algorithms are making it so that we can do parallel programming using frameworks in an incredibly easy way compared to what it once was. And generally speaking, concurrent multi-threaded applications are really hard to write. The people that write them are specialized. They know how to do certain things. There's a lot of constructs to keep in mind all the time. You have to keep track of who's using what, when, because you've got multiple threads of execution at the same time in the same process. So it takes a certain amount of formalism to do it correctly. And at best, it's going to take you a whole lot longer to write than a traditional sort of program. And the environments that run these things, such as Spark and Hadoop, have also driven the adoption. So given you now have a Spark cluster that you can go and in a few clicks spin up a cluster in the Databricks Community Edition, attach a notebook to it, write some code on it, and access some storage, it's a pretty compelling sort of thing. And I guess that's another factor probably driving this is cloud computation. I didn't necessarily add it to this slide, probably should have, because the cloud is definitely cloud plus big data and distributed processing. Those all go together. Moving over to deliverable 5. You guessed it, you're going to do some work with Spark. So the competency is to solve programs utilizing Apache Spark written in Scala. The key concept to understand here is that Spark can be interacted with by at least 4 different languages come to mind. Scala is kind of the native language because Spark was written mostly in Scala. But also you could write it in Java via a Java jar that you upload into the environment. Also interpretive languages such as Python and SQL and R can be used to write Spark jobs as well. So you have lots of different choices. So I guess 5 different choices I outlined right there. But at the end of this experience, you're going to be graded using the rubric. Do take a look at that. That's how I do grade. And your scenario here is that you're a data scientist in the fictitious company Big Data Connections, Inc. It's basically an international data clearinghouse that handles processing from thousands of customers. One of the major proficiencies is its ability to utilize Spark. And so also an interesting metric that I believe I've mentioned is that Spark is up to 100 times faster than Hadoop's MapReduce, depending upon workload and if you keep things in memory or if it spills to disk. So you're asked to come up with a marketing plan to attract clientele. You've been asked to write a short paper to be distributed at a conference. Your paper will explain how Spark can crunch massive amounts of data, revealing actionable information that will allow better problem solving and decision making. So you're asked to use the provided cellular service areas dataset to create a query to find the top 3 licensees and how many licenses each one of those licensees holds. Your results will be reported at the conference paper. So your items, and these are kind of the checklist, right? Make sure you've got a pretty good definition of what Spark is, a rationale of how it's potentially better than MapReduce, and spoiler here, it is always better performance-wise. Even if you're spilling to disk, which is the less performant way that Spark can execute, it's still going to outperform MapReduce pretty much every time, especially in scenarios where you're doing multiple passes through the data. So if you have iteration, MapReduce does not do very well at all. You have to essentially create either multiple MapReduce jobs and chain them together in some fashion. It's just not well intended for it. So you're asked to do an explanation of the high-level libraries and their capabilities. You're to come up with a definition of Spark's library components, so basically RDD, Spark SQL, Spark Structured Streaming, MLlib, and GraphX, and how each are used and kind of what they do. I would probably do a paragraph on each one of those. That would be my recommendation. Explain how the various components deal with SQL and structured data, machine learning, stream processing, and graph analytics to solve problems. And graph here is the mathematical graph, which is what GraphX is about. Includes the screenshots of your scripts and results along with a detailed explanation of your work. So this is a situation where you are expected to include code snippets in your paper as well. Some references. I would also strongly recommend you take a look at Spark: The Definitive Guide. Definitely a really good reference. The rubric for the first rubric for this is to basically all the checklist of the various items, advantages of Spark over MapReduce when working with big data, numerous examples, and it's free of errors. So examples could very well include things like iteration or multipass operations. You're not going to do machine learning in MapReduce. That's a good example. So various, and why is that the case would be the follow-on question. Shoot for that column and basically make sure there's no errors or very few, and if the errors are there, they're not terribly noticeable. Run some form of checking, either words built in checking or something like Grammarly. The second criteria, thorough detailed information on the Spark's library components. Again, these are at least a paragraph, if not a section, one for each one. And how they use, so what is the purpose of each one, and giving probably some examples of why you would use them. Not necessarily code examples on all of them, but why would you use one, and it could very well be a breakdown of the strengths and weaknesses of each. Although some of them, if you're needing a streaming solution, you're going to use Spark Streaming, right? So you would probably want to define the differences between how Spark structured streaming works with micro batches and how Spark works in a batch mode without micro batches. So that's kind of what that's kind of implicitly stating. Also make sure that you have a thoroughly detailed explanation of each of the components, how each of the components handles SQL and structured data, keeping in mind that you can oftentimes in Scala use SQL on a set of data, so on a data frame or whatever. Machine learning and stream processing graph analytics. So what are those components, how are they used in those environments? And then the last criterion is you create a query that finds the top 3 licensee and how many licenses each one holds. And you've got a screenshot of the result or some visualization of the result, as well as a description of what it means and a detailed explanation of what the query does and how it works. And with that, I've reached the end of the material I've prepared. As always, if you have questions, let me know. That's what I'm here for. If you want to shoot me an email with them or whatever works for you. So let me know if you have questions. As always, stay safe, and we'll speak again on Wednesday.